Hello and welcome to a special Giving Day SETI Live. I am your host, Beth Johnson, and I am here today with our Director of Optical SETI, Elliot Gillum, and we are here to talk about the LaserSETI project, which is an ambitious project to simultaneously observe the entire night sky looking for laser pulses from beyond the Earth-Moon system. So welcome, Elliot. Thank you for joining us today.
Hi, Beth. Nice to see you.
Nice to see you too. So we're going to talk about LaserSETI, but first I just want to give a quick shout out to our audience. Thank you for joining us today. Today we are doing a Giving Day celebration. It's a day to help support some of our specific projects. So in the case of LaserSETI, we're raising $6,000, and we'll explain sort of where that's going to go and what that's going to help us with. And if we reach that $6,000 mark today, we have a very generous donor who's going to add another $5,000. So we're very excited, and we're going to talk about what that will go to in just a minute. Please let us know where you're watching from, and we will give you some shout outs. And also don't forget that if you are watching on Facebook or Twitch or YouTube, you can use your stars, your super chats, and your bits and subs to send some money into the LaserSETI program today. So we're going to go ahead and talk about, I'm going to chase off a cat really quickly. Off, go. And he's big and he's dumb and he just really doesn't understand. He's cute though. All right. So Elliot, tell us about LaserSETI. What is this project?
Well, LaserSETI is a project, and it's an instrument, and it's a set of observatories that are designed to go around the world. It's an instrument designed to be cost-effective and have a really wide field of view in order to be able to see a huge chunk of the sky in order to look for laser pulses.
So why are we looking for laser pulses? What is the purpose of this particular search?
Well, laser pulses aren't produced by nature. It is possible, actually, I just had a post recently about a mega maser, but nature doesn't really produce lasers, and it particularly doesn't produce pulses. And so that's both something nature doesn't do, as well as things we think technology might do. Lasers are used for communication. They can be used for propulsion. They're much better at focusing light into a narrow beam than radio because their wavelength is shorter. It's a real simple equation. And so if you want to send something far, lasers are a good way to do it. And so we want to see if they're out there. That we don't know if they are, but we might as well look.
How far away can we possibly detect these?
There's really no limit, actually. We're not aware of any upper bound in terms of physics or engineering on how narrowly you could focus something and how powerful a beam you could make. So there are people who think that you could see lasers from the edge of the visible universe.
Wow. Okay, then. So what are these observatories consist of? We have two now, correct?
We do.
All right. And where are those two, and what are they made out of? What have we built?
Yeah. We have one here in Sonoma, California, at Ferguson Observatory. And it has two instruments, one looking northwest and one looking southwest over the Pacific, you can kind of think of it. And then we have two more instruments on Haleakala on Maui, and those look roughly northeast and southeast. They're looking at the same patch of sky. So we have basically two patches of sky that we're observing with these four instruments. And there's not really much to the observatory besides the instruments. There's a little bit of power and other types of equipment, but mostly it's the instrument, which is itself two cameras that one looks this way and one looks this way. And they've got some specialized optics and some specialized readout and some very specialized computers. And we look for signals that match the criteria of a single color of light on a point source on the sky that turns on and turns off at a definite point in time. It doesn't sort of slowly fade in like a, supernovae appear very quickly, but then they fade off very slowly, for instance.
Right. Okay.
We're looking for something that kind of square waves in and square waves out.
So very sudden and then very sudden off. Okay. So like a light switch almost is what we're looking for.
So
Okay.
something green or blue or red or whatever color, but it has to be, it can't be, a wide set of colors like a star produces or a glint off a satellite, because that's still just reflecting a star. It's got to be a narrow set of colors.
So how did this program come about?
That's a funny question. So yeah, it's optical SETI has changed a lot in the past couple of years. Project started unofficially probably in about 2014, where we were kicking around some ideas for different projects we could do. And I started working on the project, played with some of the different ideas. We prototyped one, and then eventually settled on this design and this set of components. And that was what, 2016 that we had a design that we could theoretically build. And then we did a crowdfunding campaign in order to raise the money to actually build them. And fortunately, we were able to, that's how we have the two observatories with two instruments each. The original goal was one instrument each, because that was kind of the minimum, was we wanted to co-observe one patch in the sky, but we were able to raise for two, which is much better because now we can actually compare the two versus only having one instance to learn from. And then we built them and deployed the first instruments to Ferguson, I think in 2018.
Mm-hmm.
And then just last August, thanks to everybody's favorite disease, we finally got the instruments on top of Maui.
So I understand there were some challenges with getting set up on Maui. Can you give us some details on that?
Sure. Well, I mean, first of all, we were about a year later. The instruments were ready, just sitting, waiting for almost a year. And most of that delay was in just waiting for travel restrictions to relax. There was also an issue in getting a case large enough to ship the things. And then ironically, we ship them. And when they arrive in Hawaii, the team calls me up and says, there's a hole. And like, okay, well, I see the picture of the hole, like, well, we'll open them up when we get there. And we open it up, and it was a single forklift puncture, which forklifts never have single things. They only do this. This was only a single hole. So clearly, and it was on the long side of the case. So it wasn't like it was an accident trying to manipulate the case. It was, clearly somebody just screwed up driving a forklift and skewered the case.
Oh,
Inside, fortunately, they didn't hit the instrument. What they did hit, though, was the transformer that converts AC power to DC power. And I thought, okay, no big deal. That's why we planned a week for this trip, even though it should only take, a day to do the main installation, because we can order a new one. It'll get here before we leave and everything will be okay. Then the problem happened that the one that we got as a replacement, instead of being a 12-volt transformer, was a 24-volt transformer that was in all ways identical, except for 1 digit or 2 digits off in the model number. And in my hurry, I didn't notice. I plugged it in, and we made a bunch of equipment unhappy. It's okay to laugh. You might as well at this point. And so we nuked some of the stuff in the instruments, and couldn't even get it on the network. So the IFA team at Hawaii, University of Hawaii Institute for Astronomy, so that's why we call that the IFA Observatory. Mm-hmm. Haleakala is kind of a long thing to say every time. They helped get it online. We figured out what was broken. I came out there, replaced stuff, and then some more stuff broke after we got the first round online. So I went out there again and replaced some more stuff. And then one more thing broke after that, but we had one of my favorite things is I didn't have to go out there and fix it myself. We had a local team member. We shipped him a replacement part, and he made the 3-hour round trip up the mountain and replaced the last thing. And the two instruments are now working smoothly, knock on wood.
Well, thank goodness. All right, I'm gonna ask you some more questions about getting set up in Hawaii, because I know I have a few more, but I want to welcome some people in. We have viewers joining us from Sweden, Kansas City, Southern California, the Netherlands, Regina in Canada, Finland, Ireland, Colorado. We have Austria and Italy joining us from some new viewers over on Twitch. So thank you for joining us over there. And once again, as a reminder, today is Giving Day here at the SETI Institute, and we are fundraising for several of our programs, including LaserSETI, which is what we're here to talk about today. The goal is to raise $6,000 for LaserSETI, and all of your Facebook stars, YouTube super chats, and Twitch bits will go to making that goal. If we reach $6,000, we do have a generous donor who will be cutting us a check for another $5,000. And all of this is so that we can deploy some more of these LaserSETI instruments into the field, because we have 2 right now. But Elliot, what's the goal? How many are we looking to have?
So it depends on how exactly you would lay them out around the world. The Earth is rather inconveniently set up for a nice homogeneous arrangement of instruments that would be easy to figure out. You know, we need dark skies, but we need power, but we don't want to be too close to the water, because then that absorbs the light from the stars. There's all sorts of things that we want, and we can't. And frankly, the Pacific Ocean is just too darn big. But despite all the things that we want, arrangements that cover the whole sky are something like 60 to 70 instruments worldwide.
Wow. Okay, so what would this $6,000 mean to you?
Well, it would make a big difference. So we are funded to build 10 more instruments and be able to cover what we think is kind of a good quarter of the Earth's sky with those 14 that we would have. And so there's a lot of things to building an instrument. There's all the 3D printed bracketry that goes into it. I think the number is something like 31 days of 3D printer time to produce all the bracketry for a single instrument. We also have the stainless steel box that's custom fabricated to fit the instrument. We have all the components that go inside, and we've already bought all of those. But one of the things that takes a lot of time, you clean the 3D printed parts, you screw it all together, you wire it all together. But you have to set up all the software on the computer. There's a lot of monitoring and control and all sorts of stuff that you have to set up. And so one of the easiest things to solve, it'd be nice to have a robot build us LaserSETI instruments, but computers are good at managing computers. And so a deployment system that we could teach the computer to build all the software. There's actually 2 computers inside the instrument. Mm-hmm. And so we can teach and frankly, there's monitoring software and also the network device that also needs to be set up, 1 per observatory. And so we can teach the computer to set all of that up for us once. And then every time we have a new instrument to a new observatory, we can just push a button, go drink coffee for an hour or 2, and we come back and the thing is all set up. And then the other benefit is that once we have that, if we're a little bit smart about how we make it, we can run it on a continual basis. We can use it to push out new versions of the software, because we do actually upgrade the software on a pretty regular basis. And today we do that by hand. And sometimes things go weird with the software. A piece of hardware misbehaves, we find a bug in the code, and so we can use it to monitor and fix those kinds of issues as well. Mm-hmm. So it would not only get the instruments in the field faster, but it would reduce our operational overhead for the instruments that we do have in the field.
So this money would be very helpful, is what you're saying, basically.
Yeah, and well, particularly since, you know, we're an extremely cost efficient project. We actually just hired our first part-time employee, but the everyone else is volunteer, and so our time is very precious in terms of how much, you know, we get done. If we can get twice as much done, then we move twice as fast, and that's going to be pretty awesome.
That sounds like a worthwhile goal to me. I'm going to give another shout out to some more viewers from, it looks like, France, Durham, England, Virginia, and Colorado. So wow, we've got a pretty decently wide audience going on here.
Is there a way that I get to travel to where they live or something? I mean, some of these places sound pretty nice, and I'd like to visit my mom in Virginia.
Oh, there you go. There you go. I guess it depends on where you want to set up some of these boxes. That's probably a good excuse. I mean, I'm how many trips to Hawaii have you had to take so far? And
Oh boy.
we all use the
Uh,
term had to take.
yeah, you know, nobody has any sympathy for work trips to Hawaii. I've learned that. I've at least gotten my wife to understand that, you know, 48 hours driving up and down the mountain and, you know, living out of what we call the blast room, which is, you know, like a concrete floor. It's it's not lying on the beach drinking umbrella drinks. Um, but it is beautiful up there. I do enjoy the time, but it's just it's a tough environment to work in. So let's see, August, October, and February. So that's and then we did a site visit to see the place for the first time, uh, 2 or 3 years ago, pre-pandemic. So I guess that's four total. But two
But
of
but
them,
as
two
you
of them,
said,
I'll own up to having fun on.
oh,
The
okay.
the, the more recent two, they were I was really tired when I got home.
Well, yeah, I understand. Our Margaret Reed, one of our associates, also traveled with you and actually has posted a journal, a blog on what the trip was like and troubleshooting the laser SETI setup itself. And so I recommend everybody go read it. It's a really good look at sort of a day in the life. Um, Out of personal curiosity, what's it like going up the mountain? I've heard from different people what it's kind of like. And did you have to how hard was it to get acclimated going up there?
Um, for me, not so bad. I've actually ridden my bike up the mountain a couple of times. It's 10,000 feet. If you do it from the ocean all the way up, I think it's 36 miles. Um, it's it's a windy road. I describe it as kind of a George Lucas movie. One of Lucas's theories on making movies is that you should have three very distinct scenes. You
Mhm.
know, think of like Endor versus Hoth. You know, they're wildly different environments, and you know, you go from the beach to these, you know, forest, to the grasslands, to this alpine scrub, and by the time you hit 9,000 feet, it's like you're on the moon. And the astronauts, the Apollo astronauts, did actually train on Haleakala because it was like the moon.
Wow.
And so it's a lot of switchbacks. um, it's tourists driving slowly in their rental cars on the switchbacks while they try to appreciate the scenery and not drive off the mountain. I can, if there were no tourists, I could probably do it in half the time as if I'm stuck behind a tourist the whole time. Um, but I mean, I love it on the bike because you get a chance to appreciate all the scenery on the way up, and then the way down is it's very well paved, and the turns are banked, and so it's a lot of fun to ride your bike down as well. That's To me, that's not a good time to look at scenery. It's a really good time to look at the road. But it's definitely a journey. It takes a long time. There's no fast way up. You got to think about like, where's my food? How do I go to the bathroom? I got to make sure I got everything covered because you're going to be up there for a while. Because it's even from the place that we stay, that's close to the summit. The institute has an old farmhouse that they rent rooms in for the staff. Um, Even from there, it's an hour round. It's an hour one way, and from basically anywhere else, it's, you know, an hour and a half or 2 hours one way.
So just to clarify, when you say the Institute has a farmhouse, it is the Institute for Astronomy, not
That's
us.
correct.
We don't. I wish we had a farmhouse in Hawaii. Okay. So I want to take some questions from the audience, and they're starting to kind of come in. So if you have questions for Elliot about the LaserSETI program, please feel free to ask. We also have some viewers watching from Mountain View here in California. Hello. And Mesa, Arizona, which I know very well. So hello to you as well. And okay. So this question, I can't pretend to be a laser expert. So I'm going to ask this question in the hopes that it is a good question. So here we go. Are the LaserSETI setups, is this a triple photo multiplier looking for nanosecond pulses?
No, that's one of the ways that I would say optical SETI, and indeed SETI in general, has changed because of LaserSETI. So traditional optical SETI theory says that if you have a G-type star from 1,000 light years away and a 1 meter aperture, that you get a million photons per second, which is only one photon per 1,000 nanoseconds, which means if you get a couple photons, if you got 7 photons within 5 nanoseconds, then that would be too many arriving, in such a short period of time. And therefore that makes a good way to signal. And the physics of that are absolutely true. But that is only one way that you could be signaled. And so what we do by combining a high speed readout as well as our transmission grating, which breaks light up spectrally, we're able to observe above that nanosecond regime. The problem is, when you're counting individual photons, you can't know where every photon came from and try to figure it out like that. And so instead of using PMTs, photomultiplier tubes, or APDs, avalanche photodiodes, which is how most optical SETI programs have been done thus far, we're using a CCD, but we read it out in a funny way that allows us to get data out of it and to have a millisecond time resolution for all the pixels coming out of the CCD. So that gets us closer to being able to distinguish a fast pulse from something that sits there for a long time, because most of the point sources are stars and they just sit there all the time, and that hurts your statistics for detection. And makes you less sensitive. If you don't do something, it makes you less sensitive to short pulses. But with this fast readout technique, we're able to get good sensitivity for shorter pulses. The other thing is, that's not that whole idea is basically an assumption that ET will figure out that this is a good way to signal, and we'll both sort of derive the same idea and meet on that idea. But there's other reasons why you might send laser pulses. And my favorite one, in terms of being the most interesting and requiring the least, is that you would use lasers for solar sail propulsion. You can accelerate a spacecraft with photons, as many projects have now demonstrated in space. And if you want to get around the galaxy, or particularly the universe, in anywhere close to the speed of light, then bringing your fuel with you is a very difficult proposition, because the faster you go, the more fuel you need, but then the more fuel you need to accelerate the fuel that you brought. And so the rocket equation shows that the faster you want to go, the exponentially harder it is. But with beamed energy propulsion, you don't have that problem. And so if you wanted to, not contact anybody and send them, comic books or whatever it is, but if you just want to get around the galaxy, because, stars expire and it's natural to explore and things like that, this is a good way to do it. It doesn't require, so you can communicate with an incredibly bright laser, but you don't need to. You can just do it for your own purposes, which is a lesser requirement. And if we saw something like that, it would be very bright, visible from a great distance. You're going to always cover the spacecraft because you wouldn't want any part of the sail not to be illuminated, because then you'd be wasting it in terms of your ability to push on it. And so that would mean you'd always have this overspill, and you'd be sweeping a path in the sky as you accelerated the spacecraft out of whatever orbit it was in. And so that's very bright, very natural, very reasonable, and doesn't require people to go, I want to contact people and I figured out the exact same idea as somebody else. So there's lots of good reasons, communications, all sorts of things why you would have lasers, but that's sort of the biggest, best, and least requirement scenario that I've come across.
Okay, that has given me something to think about. I am now deeply fascinated. Really quickly, I want to welcome our viewer who is watching from the Azores, so that's really cool. And as a reminder, just to let everybody know, we do have another SETI Live today at 2 p.m. We will be talking with the team from the Allen Telescope Array, another project that you can support today on Giving Day. And also, just so that everybody is aware, we have announced our next SETI Talks, which is on April 20th at 10 a.m. Pacific. And we're basically looking at metals and how they play a role in biology. So looking forward to that one too. All right, I've a couple more questions from the audience here. This is another technical one that I'm just going to ask you. How much beam divergence are you expecting at, say, 4 AU?
Well, we aren't so AU is the distance between the sun and the Earth. LaserSETI can distinguish sources that are up to 25 times closer than the Earth-Moon distance, but that's much shorter than the Earth-Sun distance. And so if there were a signal source only for AU further out from us or from the sun, we might see it. The beam divergence itself is kind of a middle factor. What matters to us is how many photons we get inside the instrument. So it's the photon density that matters more than where the other photons might have gone. It doesn't. If you take our largest mirror, a 10-meter Keck telescope, and you point a giant laser into it from 1,000 light years away and point it at the sun, assuming you know where the sun is going to be in 1,000 years, then the beam will expand to be the size of the orbit of Mars. You can have a bigger aperture, which means you can focus it more narrowly. You can also just stick more photons into that beam, and more will go astray. But maybe if you don't know exactly where the sun is going to be, it's not such a bad thing for the beam to be wider, because if you're trying to hit Haleakala from 1,000 light years away, that's an extremely narrow beam that would require a very large aperture, and you might want to give yourself some margin for error anyway. So it really the sensitivity for LaserSETI is fixed, but how far away they are, how narrow the beam is, how many photons per second they put into the beam, those are the parameters that we don't control. And ultimately they add up to how many photons per second do we get into the instrument that's what determines whether we can detect it. So no single parameter controls that.
Okay. One last question. This is also from our audience, and I kind of like this one. Do you have any idea what sort of maybe non-SETI science could be done with this array as well?
Yeah. So the thing we have to look through that's annoying to astronomers is the atmosphere. And the atmosphere is good for us as humans. It turns out we like breathing, we like not getting sunburns from ultraviolet radiation, and meteors also have to enter the atmosphere. And a way that, because of the ways that LaserSETI is unique in looking for short monochromatic pulses, also means that it's good at analyzing things that happen quickly in unexpected places, which would be a meteor burning up, because you don't know when or where it's going to come from. And if you do want to understand it, your standard cameras have 30 frames per second, but we have 1,000, over 1,000 actually. And your standard cameras, might see 3 colors, but because of our transmission grading, we see 30 colors. And so you can learn more about maybe what was burning up, or how it, when it broke up, or how the pieces, you can learn a lot more because we have, more than 10 times the spatial and spectral information. So we do actually have a collaboration with NASA's Asteroid Threat Assessment Program, where they study bolides, which are very bright meteors. And basically the idea for their team is, if we found, 100-meter, however big it is, if we found something that was going to hit the Earth, what we would really know is where it would hit the top of the atmosphere. But because the atmosphere significantly changes how the asteroid travels, their goal is to predict from the top of the atmosphere down to the ground. How can we figure out what's going to happen once we know where it hits the top of the atmosphere? And so LaserSETI is uniquely able to, with its wide field of view, spectral and time resolution, to capture these events and study them in greater detail than any other instrument that I'm aware of.
That's exciting too. Wow. I had no idea, and I'm really happy to hear that. Anything that helps on that kind of project is fantastic.
Planetary defense.
Yep, planetary defense and looking for laser flashes. I like this project. So if you guys are interested in supporting, we've included links in our description and also in our chats for how you can donate to the LaserSETI project today during our SETI Institute Giving Day. And I want to thank Elliot for joining us today and talking about this project. And I want to thank all of our viewers from all over the world for joining us and watching and hopefully supporting. So we're really hoping that we can get Elliot some more time to free up getting all of these things set up. So that's exciting. Once again, thank you for joining us, everybody. If you want to know more about what's going on at the SETI Institute, you can go to our website, seti.org, and sign up for our newsletter. And you will also have links to all of our various science programs there as well, if you want to find out what else we're doing. So thank you once again, everyone. Have a fabulous rest of the day, and we will hopefully see some of you back here at 2 p.m. Pacific time.